Hello everyone, this talk is about Ketu, a Kafka client we wrote in Appsflyer. We'll talk about why and how it was implemented. I'm Yonatan, a platform engineer at Appsflyer, and I work in the real-time infrastructure team, where we are responsible for production systems such as Aerospike and Apache Kafka. And I'm also part of the Appsflyer Clojure community, where Ketu was incubated, and Clojure is my favorite language. In this talk, we're going to do a quick intro to Kafka and the Appsflyer use case. I'll speak about our guidelines when approaching the creation of a Kafka client, and I'll present Ketu, the resulting client itself, its key features. And lastly, I will discuss some design and implementation choices which you might run into in other contexts. So just to illustrate the mechanics of what we're dealing with, you can picture Kafka as this ordered log of messages going left to right. These messages are actually called records, but I'll use both terms interchangeably. Each record has a numbered position on the log, also known as offset, and when you produce records into Kafka, you append them after that last offset. And so they get their own incremented offset. Of course, Kafka cluster contains multiple logs. These are called partitions, and they contain different data and offsets, which allows Kafka to distribute them and allows us as users to process them in parallel. Partitions are grouped into topics. Each topic has a unique name and will ideally contain messages of the same type. Dealing with a topic instead of individual partitions makes our lives easier, while Kafka does the heavy lifting of distribution and coordination for us. Since we can deal with multiple partitions in parallel, producers which are writing to Kafka can distribute their data and communication. And the same goes for consumers, which read the data. They do it independently of producers, and they do it independently of each other. Let's zoom in on how a consumer works. The bicycle rider represents a consuming service, reading messages from left to right, and doing some processing, then putting results into storage. It keeps consuming and consuming, and from time to time, it will commit the offsets, those that it already processed. Meaning, it actually tells Kafka the latest position in the log that it doesn't want to see again in case it restarts for any reason. And let's see it happening. It goes on and on consuming until suddenly it fails horribly. But Kafka remembers the last committed offset, which allows the consumer to restart at that position. Any of the uncommitted work done by the consumer service might be duplicated at this point, which is part of what we call at least once semantics. If we zoom out, we can see the architecture with Kafka at the center. Appsflyer is a mobile attribution and analytics platform, and we basically match between ads and the resulting installation of apps on mobile devices. And we need to provide tools to analyze ad campaigns. So each of these boxes represent dozens of services that serves this function. For example, on the upper part, we have our web handlers listening to events from all those devices, and then they produce them into Kafka for further ingestion. Some services just produce into Kafka, like those web handlers. Some will consume messages from Kafka and then push them to other systems. And some will do both. They will consume from Kafka, do some kind of processing, and produce back into Kafka. So we have these services, hundreds of them. They implement basically the same thing. We have duplication and a lot of copy-paste that diverged over time. Configurations were inconsistent. Small things like callbacks and error handling were done a bit differently over time. And we still used an old client and Kafka version. So we wanted to make a big deal out of upgrading both the Kafka clients and brokers together. This called for a library. We had our own thin wrapper already, but it wasn't enough. So we surveyed and studied a bunch of open source libraries and frameworks, as many as we could find. And what we've seen, together with our own experience and usage patterns and industry standards, we saw these repeating essentials that we'd like to have. And whichever library we choose should provide these essentials. First of them is what's known as a source. It is basically a loop that endlessly consumes messages from Kafka and provides these messages for you to process in a continuous manner. Then, in the other direction, there is a sink. It's a producer loop, which you continuously provide with messages, and it will eventually write them into Kafka for as long as it runs. We want consuming, producing, and the processing in between to run concurrently. Obviously, consuming a message will happen before processing that same message and producing a result, but these three processes shouldn't necessarily wait for each other in each individual message, as you can see on the synchronous process on the left. This concurrency requires back pressure. The synchronous process on the left will naturally defer the next operation while the current one is executing, but concurrent processes will have to coordinate somehow so that slowness downstream will propagate upstream. You can see on the right, if producing to Kafka is slow, there is no point processing messages at full speed. As a consequence, we'd also like to back off consuming from Kafka. Of course, something always fails, but it's not always obvious when it failed or how to handle the situation. What do you do when the consumer throws an exception or when the producer indicates a failure 20 seconds after an async operation started? We need the correct choices implemented and expose them as a consistent API. So our guiding principles for any library we might choose are some ideals and constraints we have as user base on top of these essentials, and they will steer us in the direction of the eventual product. So first and foremost is high throughput. This is our prime directive. We're dealing with mass processing of events, which I've included the numbers previously. So if it's not a high throughput use case, it has less of a priority for us at this time, and it might even interfere. High throughput requires minimizing interference while processing messages. Unfortunately, features are interference. So any feature that can be optional is optional. Things like data transformations, results handling, serialization, any extra behaviors, these all should be optional. We are embracing channels as an API and specifically core async. This is our opinionated part, and it brings with it a specific execution model. You can still decide not to use core async, of course, but it would leave you with the bare essentials and without streaming behavior. In addition, we already use channels everywhere in Appsflyer, so this choice will maximize adoption. And because nuances and bugs in core async affect external behavior, those become part of the expected, of what is expected and we rely on, and part of our API. So until we learn more, we will not put core async behind an abstraction, and we will not pretend to be able to replace it. We also embrace the Java client, Kafka client, and we don't hide this implementation detail at all. We'd like to configure this client the same way you would in Java code. And that way, prior experience with the Java API, which is very common, is still relevant. Of course, we get all the improvements and bug fixes it gets from Confluent over time. Metrics and third-party integrations are still relevant. and existing documentation is relevant, which saves us a lot of time. The other side of that coin is that we don't re-implement these things. We don't re-implement core async, and we don't re-implement Kafka delivery semantics. Core async has its known behavior and nuances, which users expect and rely on. And of course, we don't want channels with the do networking, for example, as this will be misleading and against the language of the system and all that. And regarding Kafka, it already has known delivery semantics, like at least once, retries, how it does timeouts, etc. We don't want to introduce things like manual retries or writing to local disk and only then sending to Kafka. It changes semantics, more things can fail, and it complicates the performance model when you want to debug your service. So we surveyed all these libraries, everything we could find at the time, and they just didn't fit our guidelines. It's not to say that they aren't any good, but only that they were not meant for us. Some of the reasons are they were wrapping a very old Java client and we wanted to upgrade. They were poorly maintained or totally abandoned. Some of them declare themselves as not production ready. Some have like other libraries as dependencies, which could be optional, like JSON serialization. We don't necessarily need that. They had hard-coded Java to Clojure transformations, which we would like to have as optional. They had no control over channel creation, no error handling, or they were nice, but they solved a problem that we don't have. So we ended up with Ketu. Let's introduce it with some examples. They will be minimal and syntactically incorrect for presentation purposes, so please bear with me. The first thing you want to do is consume from Kafka. Suppose I have a topic full of names and I want to get and process these names. I don't want any metadata, such as offset or the time it was written, etc., only the name. And names are, of course, strings, so I want them as strings instead of the raw bytes residing in Kafka. Since we use core async, I'd like to get these strings from a channel, so I create one. And then I combine these into a consumer source that continuously provides messages into the channel. All we have left is to take items from this channel, and as you can see, we got exactly what we've asked for, a simple string of a name, Alice. On the other direction, we have exactly the same topic full of names, but this time we'd like to add new names on top of the existing ones. So the configuration is the same, the channel is another channel, but it's the same concept. But this time we will put names into the channel instead of taking from it. So I create a producer sync that continuously sends Kafka whatever I put on the channel. All is left to do is to actually put a name into the channel, and Bob will eventually find its way into Kafka. Essentially, this is it, the essence of the API. This is exactly the point of using core async. We just take and put things on the channels. But even this minimal API raises many issues and dilemmas, which I will show later. Let's first see another key feature of Ketu, which is shapes. Let's take, for example, the consumer record object, which we get from the Java client. It has the actual record value and some metadata fields, but it's not necessarily what we want to get, right, from the channel. It's an ugly Java object, and we, as Clojure developers, maybe want something more palatable, like a vector or a map. If you recall, in the first example, we configured shape to be the value only. And indeed, we got a simple value field of the consumer record. which contain the name Alice. So let's focus on that, just on the shape configuration and the resulting value we get from the channel. Instead of just a value, we are not limited to a single one. We can also ask for multiple fields of this record. And in this example, we want a tuple containing the value and offset fields of the record. We use tuple to mean a vector of predefined elements, and this data-oriented style for defining the shape is inspired actually by Mali schemas, where the definition first contains the type of data structure that you want to see in the channel, and then the selected elements you want in that data structure. And you can see the result is exactly that, a vector with a name and the offset in Kafka. Similarly, a shape of map will result in a Clojure map with each selected field translated to a map entry. We can also register custom shapes that accept configuration at runtime. And in this example, we want the cake output, so we configure it with a specific mold. Cake is the name of the shape, and the mold is the parameter configuring the shape. So how it is implemented? At configuration time, Ketu will provide us with the shape parameter, and this is our chance to create a transformation function of the record once at runtime, according to these parameters. Our dynamic function will then be invoked over and over for each record we get from Kafka. We did try to avoid this amount of functional indirection and head scratching, but in this case, it was necessary. This is also how we implemented the built-in shapes, vector and map. We just register the shape with a function that returns a function. In this case, to save some overhead when constructing the data structure, we use eval to create the most direct function that we can get. So ultimately, the function just returns a vector literal or a map literal, which is the fastest option. Again, I'm sorry for the head scratching. I was hacking at it until it worked, and I don't want to look at it ever again. If you don't like any of this, you can just directly configure the shape to be a function of the record, in which case the result will, in the channel, will be the result of the function applied to the record. Of course, there's the other direction of the producer, which that uses the Java object of type producer record, but it's everything I've said is applicable there as well, so we will not show it here. We have more features in progress, like managing offsets and providing very detailed results handling. But as you'll see next, each feature creates a lot of questions and things to think about. So this will take time to implement. Dilemmas are the sort of questions we ran into while implementing Ketu. You'll see that you can always dig deeper and suggest more alternatives for each decision. For example, how do we put the things we get from Kafka into the channel? We do this by we get from Kafka messages by polling for more and more messages, which we get in the form of a collection. As you see, the basic Java function is poll, which returns a collection. Earlier, though, you've seen that the channel contains individual messages, but some users might prefer the original collection that we get here for various reasons. Some of them might be performance or the way they are used to do things. So let's see how it looks. On the left side, we are polling for messages from Kafka and get a collection that we put as is into the channel. We can immediately continue to the next loop iteration and get another collection from Kafka, which we put on the channel. And then one last time, we get a third collection. And only then we run into back pressure. On the right side, we again get a collection from Kafka, but this time we iterate over the collection. We put each message individually into the collection, and the back pressure is applied when we can no longer fit more individual messages. And on the right side, it means we read from Kafka only once instead of 3 times. So depending on our decision, the channel will contain different kinds of inputs, and the user will have to process them differently. And also back pressure will mean 2 different things. Then there's also the question of the cat transducer. What is it, and should we use it for optimizations or other reasons? Cat is an expanding transducer, which means when we create a channel with cat and put a collection in the channel, the collection will spread into individual messages inside the channel. On the other hand, on the one hand, it has a performance benefit of acquiring the channel lock just once for the entire collection. Instead, on each individual message go through the barrier. But you can see on the right side, it causes the buffer size to grow and breathe, so to speak, since it also shrinks according to how the user interacts with the channel. This changes back pressure semantics, and also while we were internally discussing it, there was still a bug in core async that made the buffer grow endlessly. So it's not like everything is perfect all the time. You have to read the source code of everything you use, and it's not that simple. Going back to the shape feature, this is another dilemma. The shape option is a function of a single record, as I've explained before. But now we are talking about putting whole collections as is into the channel. So will the shape be a function of the whole collection? How will it play with the transducers? We will probably eventually enable all of the options and let users compose them as they will. Another dilemma was how to handle graceful shutdown. Let's talk about it as defensive programming. We have seen before that the consumer source puts messages into the channel until the buffer is full. Once it's full, we have a pending put, waiting for the user on the other side to take from the channel and relieve some of the back pressure so we can take more and more messages from Kafka. Now, suppose the user wants to shut down the service completely. A well-behaving user will first close the consumer source, let it finish consuming, and then drain the channel from inputs. This will release the consumer that was previously stuck on pending put operation and will allow the consumer to close itself gracefully. However, if the user is misbehaving and first stops processing this channel and then tries to close the consumer source, nobody will drain the channel and the consumer will be stuck forever. One way of avoiding this is to use alts with a dedicated release channel. And when the user closes the consumer, we will release the operation ourselves instead of being stuck. And there's more than one way of doing this. We don't have to use alts, perhaps, and there are performance issues to consider with alts because it is much slower than a direct put operation. All of these dilemmas are relevant to this single tiny line of code, and it was very humbling to see how the amount of options just explode on each decision points. Another question was whether we want unqualified or fully qualified namespace keywords. We went for mostly unnamespace keywords. Frankly, it looks better also in JSON, which we use for configuration. It's very minimalistic, and it isn't actually that bad, as bad as you might think. We have more and more dilemmas, a lot of them. I will not go into them right now. And this is a good point to acknowledge all the inspirational libraries and all the alternatives out there. And of course, to thank Clojure itself, Apache Kafka itself, and my employer Appsflyer for giving me the time to work on Ketu. Thank you very much. Don't forget to check out Ketu on GitHub, and you can always reach out on Twitter or Clojurians.
Thank you.